Scientific notation. A number is written in scientific notation if it has the form n times 10 to the k, where k is an integer and the absolute value of n is between 1 and 10, or is equal to 1. For standard notation, if k is positive, we multiply n by 10k times and hence move the decimal point k places to the right. If k is negative, we divide n by 10k times and hence move the decimal point k places to the left. I used to have such a hard time with this, mainly because I was always wondering whose left hand and whose right hand I was going to move it towards, mine or my instructors. And it does get a little bit of a confusing at a certain point. So let's try this out. Let's see if we can simplify this. So if k, in other words the exponent, so if k is positive, then the original number is bigger than 1. So if k is positive, then the original number is bigger than 1. That's probably the basics. The very bottom line that we have to remember. Having a positive k means you have a number bigger than 1. Positive exponent. So if k, once again the exponent, is negative, then the original number is a decimal number. So if k is the exponent, then the negative number, original number, is a decimal, typically smaller than 1. So be aware of that. So number between 0 and 1, in other words. Okay, so let's see if we can try some examples to make it a little bit easier. So let's realize that those are the k values that we're talking about. This is the exponents, the 6 and the negative 5. So examples, write the following in standard notation. So for A, we have 8.31 times 10 to the 6, and for B, we have 6.488 times 10 to the negative 5. And once again, be aware that 6 and the negative 5 is the k's or exponents that we are talking about, that define the location or the number size, I should say. So for A, we have 8.31 times 10 to the power of 6. And let's realize x means multiplication in the language of scientific notation. So scientific notation, you use x as a multiplication. I would recommend using a big dot if possible, but otherwise x would be fine. Okay, as long as it's only for scientific notation. Otherwise you're going to confuse it with any other applications. So that means we're trying this out, so do not copy this yet. 8.31. Well, let's see. We have a positive exponent. And let's say by accident I went the wrong direction. There we go. So that means I moved my decimal point from the original location, which was between the 8 and the 3. I moved it once, twice, 3, 4, 5, and finally 6 times. I moved my decimal point 6 places, but I moved them to the left. Remember, positive exponents, they move to the right because it becomes a positive. So I don't want to remember whether it's right or left. What I want to remember is it bigger than 1? That makes it really easy, agreed? Is this number that we got bigger than 1? No, obviously we can see it's a decimal number. It's a really small number by comparison to 1. So in that case, it looks like we went the wrong direction. Time to erase. So, eraser. There we go. Or you can call it your erasing theorem. So 8.31. If we move it once, there the decimal place would move there. Twice, well, I may need to add zeros to this, and we can add as many zeros as we need to in this case. So whenever there's no numbers following decimal points, so after the decimal points to the right side of it, in other words, you can add as many zeros as you choose. You can add as many zeros as you choose to the left side as well after the 8, or before the 8 actually, but it wouldn't help typically, okay? So be aware of that. But to the right, it helps. So there we go, adding another 0. So far we moved it once, twice, 3 times, 4, 5, and finally 6 places. So move this 6 places. Notice we have the 3, the 1, and 4 zeros. That makes it 6 places that we moved it. Agreed? So that's where our location for our decimal point is finally, after moving it 6 places. And in this case, we could see that once we finish moving the decimal point, we're going to get a number that's significantly bigger than 1. Agreed? So hence the positive exponent. So in other words, let's get rid of the decimal point between the 8 and the 3, because now its location for standard notation is at the very end. So let's try to make this number easier to visualize by putting commas in the right spots. So there we go. Putting the commas in the right places. Now we can see that this number is 8,310,000. So it's a pretty large number by comparison to 1. And remember that the exponent, being positive, tells us that a number is bigger than 1. Agreed? We definitely have a number bigger than 1. Okay, so once again, just a real quick check. Is the number bigger than 1? Yes, definitely. It is bigger than 1. So that's why we got a positive exponent. So since the number is bigger than 1, it's correct. 8,310,000 is the correct standard notation value of 8.31 times 10 to the power of 6. Positive 6, right? Let's go for the next one. B. 6.488 times 10 to the power of negative 5. And let's remember that the x implies multiplication. Agreed? You're welcome to try this on your calculator, actually. You can put it on your calculator. We'll try later. And let's realize that in this case we have a negative exponent. So we have a negative exponent. So start with 6.488. If I move to the right, I'm going to get a number larger than 1. But we're supposed to be getting a number that's smaller than 1 because it's a negative exponent. So that means if I move it in this direction, 1, 2 times, but now I need to add zeros. Agreed? So let's add zeros as we go. So in this case it's helpful to add zeros, but that's because our decimal point is moving to the left. So we're going to move the 2 places so far. 3, and add another 0. 4, add another 0. 5, add another 0. And finally, we're done, right? That was 5 places. So we need to move it 5 places to the left in this case. And we notice this because it gave us a number that's smaller than 1. So finally, putting a decimal at the end where our last 0 was added. There we go. So there it is. 0.00006488 is our number. Be aware, I like to see a 0 at the beginning. It makes it useful because you get to place the ones location, the unique location of ones. But many instructors may not, okay? So it depends on your instructor. It also depends on the number of significant figures that you use. But for me, I'm going to add a 0 at the beginning. Just an extra 0. It has nothing to do with the scientific notation, so be aware of that. It makes it easier to visualize, though, that I have a dot in there. Otherwise, the dot seems to disappear. So once again, 0.00006488 is our value. Notice I didn't mention the first 0. Okay, that's our final answer for that one. So let's go to the next one. Compared to scientific notation, A, we have 280,000. Notice I got rid of the commas. We want to avoid the commas because otherwise they become confusing, okay? So just the number without commas. And we want to convert to scientific notation. There is no decimal point. Whenever there is no decimal point, you always put it at the very end of that number. So at the right side of it. If there is no decimal point, place it at the last place, at the right side of it. So once again, if no decimal, place here at the end. And now let's try to convert it to scientific notation. And scientific notation normally has 3 significant figures. So 3 numbers that you're going to take care. But be aware of this. Depending on who you work for or who your instructor is, you may need more or less numbers. For instance, if you work for NASA, you probably want to use more significant numbers, right? Maybe, I would assume. And let's realize we want to have a decimal point after the first significant figure. And then we have a times 10 to the power of something, so some exponent, depending on what the number is. Once again, note that I have the decimal place or decimal point after the first significant digit, okay? So those boxes implies that that's where we're going to replace them. In this case, the very first significant digit that I can see is the 2. The 2 is a significant digit, agreed? So let's put the 2 there. Followed by the 8 is the next significant digit. And 0, well, 0 is not really significant if it's followed by other zeros. But if it's not followed by other zeros, we would have to round that next number. But in this case, it's a 0. So once again, it's not significant. We're going to omit it at the end on our result. But be aware, we're still putting it there so you can see it. Okay, so how many places did I need to move that decimal point in order to get it between the 2 and the 8? Let's see. You can visually see it on your screen or move your finger along the screen, right? So 1, 2, 3, 4, 5 places if you move your finger along the screen, right? So it means my exponent is a 5. My original number, was it bigger than 1 or smaller than 1? 280,000. Definitely bigger than 1. So it's a positive exponent. So our number has a positive exponent. So finally, our answer becomes 2.80 times 10 to the power of 5. Once again, the 0 is not significant, agreed? So we're going to omit the 0. Oh, a slight trace of our 5 was left, but that's okay. So converting it to just 2.8 times 10 to the power of 5, agreed? And there we go. That gets rid of a trace. So 2.8, since the 0 is not significant, we omitted it. So 2.8 times 10 to the power of positive 5 would be our final answer. Let's go for the last one there. B. Capital B, I should say. Okay, in this case we have a negative and we have a 0 before the decimal point, but that one's not significant since it's just locating the ones place. But the following ones are significant. So 0.00000023. Okay? So in this case, once again, just as before, scientific notation, we have 1, 2, 3. 3 decimal, or 3 significant figures, agreed? Okay, so a decimal after the first one, and times 10 to some power afterwards. Do realize the decimal point in this case goes between the 2 and the 3, right? Because the zeros are not significant. So, therefore, we were going to use that location. So there's your 2, the 3, and there's nothing after the 3. Remember, you can add as many zeros as you choose to after that number because it's a decimal value, agreed? So you can add as many zeros, but I only need 1. So I'm going to add an extra 0. There we go, because I only need just 1. I could add 2, 3, 4, or 5 zeros if needed, if it's required by your instructor or your boss, right? But in this case, just add in 1 for the basic format of the scientific notation. And let's realize that we moved the 1, 2, 3, 4, 5, 6, and 7 places. We moved it 7 places. So therefore our exponent is, and we moved it, well, originally it was a negative number, right? Well, I should say a decimal number, pardon me. Originally it was a decimal number. So that means we have it as a negative exponent, and it's a negative, we counted 7 spaces, right, that we moved it. So it's a negative 7. So that means finally our result, or scientific notation answer, would be 2.3 times 10 to the power of negative 7. Hooray, we're done, right? Take a look back at our original number. Negative point and then several zeros, 2, 3 at the end, right? So it became 2.3 times 10 to the negative 7. Did you notice that? We're not done yet, right? What are we missing? We're missing something. Do notice the fact that we have a negative sign on the exponent has nothing to do with the negative number. This is a negative number to begin with, so we need a negative sign. So there we go, negative 2.3 times 10 to the negative 7. Once again, that negative on the 7 has nothing to do with the number. It just tells us that it's a decimal number originally. In scientific notation, we still want to keep the number as either being positive or negative, right? So in this case, it's a negative number, so we have to include that negative sign. So now we're finally done. That is our final answer, negative 2.3 times 10 to the negative 7.